Hello and welcome to part 6 of Dev Maths and Stats Refresher Course, Lecture 5. We move on now to looking at second order conditions to tell whether you have a maximum or a minimum or something else. If you watched the last part of the previous section, you'll see that without the second order conditions, it takes quite a long while, a lot of calculation to work out whether you have a maximum or minimum or nothing. So we need better conditions, a better system for doing that, and that's called the second order conditions. So the first order conditions are necessary, but they're not sufficient conditions to have an extrema. If you find a critical point where the first derivatives are 0, you may have a maximum, you may have a minimum, or it could be nothing. The second order conditions tell you more. So to understand how these conditions work, we're going to take a close look at differentials, including second order differentials. Now this, as advanced warning, this section on second order conditions has probably got some of the hardest conceptual stuff and the most awkward and complicated looking equations. But this is explaining how the method works. If you just want to know how to use the method, at the end you get some simple method you can just apply. So a lot of this section is the background logic to why it works. So it's again like knowing how a car works or whatever. It's useful to know, but it's not completely essential. So don't worry if you don't follow all the details, especially when we get onto more than one variable. So what we're going to do is take a single variable function first, two variable function next, and then hope you can see how it generalizes. So here's our one variable function, and it's start with the cubic, and as well as this we need the first derivative, so we differentiate that. Okay, now to go over some old ground again, what we have seen is we can get a linear estimate of how f of x is changing from an initial starting point using differentials. Now, so a differential change depends on where you start and how far you go. So you can think of dz as being a function of x, the starting point, and dx, how far you're going to move. So this linear estimate dz, the linear estimate of how f is going to change, depends on where you start, how far you move, and it's given by the derivative with respect to x times the distance you move. So it's the gradient times the distance you move. So on an example function, if we started at 2 and we went forward a step of 1, we'd estimate the value at 2 plus 1, estimate the value at 3. And to estimate this value at 3, you need the initial value at 2, you need the gradient at 2, and then to test how you did, you need the actual value. So these are the three things. So 289, 221, 450. So the original values at point 2 is 289. This is the gradient 281. So according to the formula, to predict the value of the increase in z from the point 2 moving forward 1, it's the gradient at z, the gradient at that point, which is 221, times the 1. So that's the gradient times the step, which is 1, equals 221. So the change from 2 to 3 should be 221. So if we start with 289 and add on 221, we get 510. The correct value is 450. So we have overestimated. So let's just see, you've seen this already, but this is why we overestimated. So we started from 2, went forward 1, we estimated to here, but really it should have been here, so it's an overestimate. Great. So note that you could also use the same thing to work out the change going from 2 and going backwards 1 to 1. So starting from 2 and going a step of negative 1. If you did that, it would be 221 times negative 1 is negative 221 because the gradients are the same backwards. So that you would overestimate the value here as well because it would be this instead of this. Okay, now so far so good, but the idea of the second order condition test, it's called second order because what you're seeing is you're predicting what's going to happen to these predicted changes. As you move away from this initial point, is this predicted change going to increase or decrease? for example, if we move away from the point 2 to the point 3, so starting at point 3, we want to predict from 3 to 4. So predict from here to here. Then you'd be calculating dz from 3 going forward to step of 1. So we need the derivative here at point 3. So we'd be predicting that it goes up by 105. So instead of predicting that it's going to increase by 221, we predict that it will increase by 105 because the slope is reducing. So if the estimated increase is smaller at 3 than it is at 2, then the slope must be decreasing, which means the graph must be concave. So because dz is getting smaller, the graph must be concave, which means if you can find a point where the gradient is 0, you must then be at a maximum. The problem is you don't want to test where you're looking at 2 and then looking at a separate point, because on a complicated graph anything can happen between these two. So that's no good. We need a test which is only based on the values of the function and the derivatives at the point 2 itself. So this is where it gets slightly complicated. What you want to do is, just as dz estimates the change in the function, now you want to estimate the change in dz. So it's an estimate of the change in dz, and dz is itself an estimated change. This is where the second order word comes in. So you're finding a linear estimate of a linear estimate of the linear estimate of the change in f. Okay. So at the point 2, this is our prediction at 2. Starting from 2, you go forwards like that. Starting at 3, you go forwards like that. So the way it's changed between 2 and 3 is to subtract these two. Subtract these two, and you find that what's happened is it's the change in the gradients of the thing that's caused the change in the prediction. So what we need to do is to predict what's happening to the gradients here, this f of x. So predicting how the derivative is changing. So just like we can get a linear estimate of the actual function using the value of the function's derivative, we can get an estimate of the function's derivative using the derivative of the derivative. Because the derivative is just a function, so you can apply the same thing and use the same rules. So the formula gives you that the predicted change in the derivative is equal to the derivative of the derivative times the step forward. That estimates this change in the derivative, and then you substitute this back in for this up here. So this becomes equal to the estimated change here becomes equal to this part. So you have the derivative of the derivative times 1. That's how much you estimate the derivative change, times 1. And that's how much you think the predicted change is going to change. So this is the predicted change in the predicted change, which is why it's second order. And this part here literally is 1 times 1. So the D2 means second order, differential of differential. It's like an operation on an operation, or a function of a function. To apply this, in this case, you need to work out the second derivative. So if you start with f dash and then differentiate again, so that was the original derivative, first derivative. So differentiate this again. Find 24x minus 176, and then substitute in the point x is 2. And here we have negative 128. So this is predicting that dz will fall by 128. In actual fact, dz fell from here to here, fell by 116. So we overestimate the decline. It's never exact, it's a linear estimate. But the important thing is that it's negative. Because it's negative, it's showing that this was going to decrease. So the graph was concave at axis 2. And this is just based on the point 2. We're no longer looking ahead to 3. It's just predicting what's going to happen to that derivative from the point 2. So after all that words, you'll see that all you really need to do is to look at the second derivative. So here's the general formula. if you apply this to anywhere, if you look at formula equation C here, where has C's gone to? Oops. Yeah, this part here. For a general function, well, this is already a general function, but here this is the distances. This is dx and dx, the distance you're moving forward. So this is dx times dx, which is dx squared. So that's why you have, oops, can see fire. So that's why you have dx times dx, which is dx squared. So you can interpret this to mean that if this is always negative, it means it's concave. If it's always positive, it means it must be convex, so it's a local minimum. If that's absolutely everywhere, it's a global maximum and minimum. If it's 0, then it's indeterminate. You might have inflection or saddle points. Now with one variable, and only with one variable, because this dx squared is literally a number squared, this must be positive. So you can tell if this is negative or positive by only looking at this. This is positive, that must be positive. If this is negative, this must be negative. That only works with a single variable case. So what you really need to do is to look at the sign of this. So if this is negative, you've got a maximum. If it's positive, you've got a minimum.